It's really fun to be here. I changed the title of my talk, so I hope that's not too much of a shock for you guys. So I'm calling it Crowdsourcing for Machine Learning. And why am I doing that? Because like everywhere I go, it's like everything seems to be machine learning these days. Even on NPR, I can't, there's not a company that's not doing machine learning, big data, cloud, whatever. And so machine learning is great, and it's all about getting data, lots and lots of data. And in fact, that's led to a huge rise in crowdsourcing with a number of different labor platforms out there. But there's like one thing that people seem to forget when they use crowdsourcing to get machine learning annotated training data, and that is that the data that we tend to get is actually used for two different purposes. So one purpose is training data, which of course is what you need most of the data for. And the other one is test data or validation data. And with the data that's used for test and validation, the accuracy of the data is super important, which leads to lots of people trying to do really high quality annotation and sometimes get multiple people annotating the same examples and using majority vote or expectation maximization to come up with the most accurate labels. When you're actually creating training data, that can be a mistake because we really don't care about the accuracy of the training data. We care about what's the accuracy of the resulting classifier. So what I'm going to do today is talk about a number of different crowdsourcing techniques. Some of them are especially good for getting accurate data. Some of them are more emphasized on just how do we actually train a good machine learning classifier. So that's the two halves of the talk, not quite halves. The first part is a little bit longer. So I'll be talking about a couple different techniques for generating really accurate data. One is by using decision theory. Another one is by getting workers to argue with each other. And the third one is trying to get the workers to actually improve the instructions of the workflow that they're using themselves. And then the final little bit in the talk is going to be about something called reactive learning, which is a crowdsourcing technique that's specifically aimed at building high-quality classifiers. OK, so I'll start out by talking about decision theory. And I'm going to use an arbitrary workflow to explain this. This is actually the iterative improvement workflow from Greg Little's PhD thesis that Lydia helped develop. So here the basic idea is you have some sort of initial artifact, could be a caption for an image, and maybe you ask a worker to improve it, and then you go out to some other workers and you say, well, which of these two captions is better? And then you take the better one, and you either give it out or else you send it back through to get it improved more. And in Greg's thesis, he started out, for example, with a captioning task. Here's a picture. That's what the crowd worker came up with as the first explanation, a first caption for the image. And after going around 8 iterations, you get a much, much better caption. It's really pretty cool that crowdsourcing can do this kind of stuff. But this is Greg's thesis, so I will skip after it and just point out that while this is really powerful, there's a whole set of questions that Greg didn't really answer. One is, how many people should you have vote on which of these two captions is better before you go around the loop? And how many times should you go around the loop? And Greg used some pretty heuristic techniques for the votes. What he did was he got 2 different votes. And if they agreed, he figured that was the right answer. And if they disagreed, he got a 3rd vote to disambiguate, took majority vote, and went around. And then just went around the loop the same number of times every time. Pretty simple approach. But what I want to address is, can we do better by actually varying those answers to those questions? So I'm going to think about using decision theory to figure out what's the best thing to ask the crowd worker to do. So the crowd worker, we could ask them to vote on 2 different captions, or we could ask them to go ahead and improve whatever we think is the best caption so far, or we could just decide we're done as well as we can. Let's just submit the final result. So I'm going to treat this as an AI planning problem. So in AI, typically we've got an AI system, an agent that's interacting with the environment. Here, the environment is giving percepts, and that's going to be the result of the crowd workers' efforts. And the actions are to ask people to do things for the agent. And to control things, we're going to use a partially observable Markov decision process. So let me just do, since I know we've got mostly an HCI audience, I'm going to just go very, very briefly over what Markov decision processes are. So here we've got a world state, suppose it's for a robot moving around in a 2D environment. We've got a set of actions, and what the actions is says, suppose we're in some state and we execute an action, then we've got a probability distribution over where the robot is going to end up, which is visually shown by that pink region there, and some cost for the action. And then after the robot actually does the motion, we get to observe exactly where the robot is, and we get some sort of reward. And the objective is to come up with a policy which tells the robot always what to do, given some state, what action should I execute, that's going to maximize the expected discounted reward of all of the rewards we're going to achieve over time. So that's an MDP. And people should ask questions. If anybody's got questions, please speak up at any time. We're going to use, and right, this is easy if you know what those probability distributions are and what the rewards are, but typically what we do is we don't know that, so we want to learn them as we're actually generating that policy. What I actually want to use is a special kind of MDP called a partially observable MDP, and it's got the same thing, except we start out with a probability distribution over the state. We don't know actually where the robot is, just where it probably is. We got the same action model, but after we execute an action, we get, instead of seeing where the robot is exactly, we get to have a noisy sensor reading, which allows us to come up with an improved probability distribution, but we still don't know exactly the state of the system. And we're still trying to come up with a policy, and we're still doing that while we're learning the action model. So this is a POMDP. Okay, so that sort of makes sense in the context of robots, so let me explain how it works for crowdsourcing. With crowdsourcing, instead of having actions like moving and grasping, we've got actions like improve the caption or vote which of the two captions is better. The state space, instead of being an XY coordinate for the robot, we still use a state space, in this case, of two real numbers. And they're basically representing the quality of the first caption and the quality of the second caption. So our numbers have to be between 0 and 1. Instead of having a sonar, all we get to observe is what's the result of the most recent vote. And the reward is, well, we have a negative reward every time we pay a worker, but we get a positive reward for returning a good caption at the end. So that's the POMDP model. And just to give an illustration, so here's what happens when a worker creates a new artifact. So we might have some distribution shown at the top that says, you know, we think the caption is not so good. And after we ask a worker to create the new artifact, well, then maybe we've got an expectation that the caption's quite a bit better. And here, if we've got two different captions and we've got distributions over both of them, and we ask a worker which one's better, supposing the worker says that the first one, artifact 1, is better, then that gives us these two different distributions. So basically that means that either this caption is better or else this caption is worse. And so we update both of those probability distributions. And we learn these models over time. Okay, so that's how, any questions so far? Okay. There's a bunch of AI techniques for solving these things. They all revolve around Bellman's equations, and fundamental to reinforcement learning is solving this exploration trade-off. And I'm going to skip over all of these techniques because they're more AI techniques than HCI techniques. Here's the results when we applied this and compared it to the model that Greg used. So first of all, with a POMDP, we're able to generate much higher quality captions for the same cost. Or if we control for the quality, then we're able to generate them at much reduced cost. So 30% less labor. That's kind of cool. What's more interesting, though, is actually what the system does. So this is what Greg's system did. And notice how many iterations we're going over, and also notice how many votes are happening. Roughly, it's like 2.5 votes, right? That's because he went out and asked 2 workers, and if they agreed, he stopped. Otherwise, the system asked a third person to disambiguate. What our system did was this. And when I first saw that, I thought that there was a bug in the code. And then we realized system actually is being very, very smart. It's not wasting any votes at the beginning because it's just assuming that the worker probably did improve the caption. And it's only after you've had a whole bunch of people improving the caption that it starts getting hard to make it any better. So that's where it started allocating more and more of the effort to try to figure out what's the best caption. As a result, it's able to make better decisions over here and also able to go out for more iterations. And that's why it came up with better captions. So that's kind of cool. Yeah.
How exactly did you go about the data, like the training part of the policy?
Yeah, so this work that I'm describing here sort of as a preamble to the rest of the stuff is things we did quite a few years ago now. We actually learned the probability models using supervised learning. So we had a separate set of tasks where we learned them. So in these experiments, we did an offline learning process to learn the probability models. What we did in the subsequent work, and so all the other things I'll be talking about after this are all done with reinforcement learning. So as you're actually executing the workflow, you use expectation maximization to build up these models of what the actions are doing. Explaining the details takes a little bit of time, so happy to do that afterwards.
Did you need a lot of episodes to learn something substantial, or was it 10?
So let me give you an illustration with the reinforcement learning approach as we're coming up. A slightly different task, but it answers that question directly. Okay, so I want to get back to annotating training data because lots of my NLP colleagues at UW are especially interested in doing this. So the problem, of course, is that the annotators make mistakes. And so what most people tend to do is they filter out with gold questions. They ask workers to do the same thing multiple times as we saw before. They aggregate with expectation maximization. They pay lots and lots of money, and still they tend to be disappointed with the results. But let's just look at one of these things. So one way of making sure that your annotators are doing a good job is to ask them questions where you know the answer already and see whether they get the answer right. Question is like, how many questions, these questions where you already know the answer are called gold questions, how many of the gold questions should you insert? And just picking a couple papers from, actually 2 of them were done here at Stanford, and people do all sorts of different things, 13% gold, and filter them if they get less than a 67% accuracy rating or whatever. You can see that there's a complicated set of parameters to figure out to try to balance off, and people oftentimes do a bunch of studies at the beginning to try to figure out whether they're getting the data right and so on. But the bottom line is, not only is it a hassle to come up with these parameter values, but there really is no right answer to that question. It's much better not to have a static policy, but instead be adaptive to the workers and how the workers are behaving as things are actually behaving. Because maybe at different times of day, you need to have a different policy. Yeah.
Could this also just be task differences? What? Could it be task differences here more so than worker differences?
On the previous slide?
Well,
or here.
In this case, like, you know,
task differences, I think, yeah, some problems are going to be much, much harder, and so maybe you want to maybe you need to be testing the workers more. So I agree. I don't think even within a single task there's an optimal set of parameter values, but I think that it's really going to change between the tasks as you're suggesting, which is why it's so hard to come up with the right values. And again, like what Crowdflower says is, you know, put in 20% of all the tasks you ask workers to do should be test questions where you already know the answer. Wow, well, that's actually wasting a lot of money if, you know, especially now if you want the other people to do it 3 times, and it's really kind of crazy. Okay, so it shouldn't be a surprise that what I'm proposing is that what we should do is give out these tests adaptively, and we can use a POMDP to figure out how to do it. So the basic idea is we basically say, what accuracy do we want the actual data to be? We provide a bunch of gold questions and a base policy, which could be the Crowdflower default policy of putting in 20% gold. And then the system has got a series of questions. So I could ask a test question, I could ask a real question where I care about the answer, or I could just tell the worker, sorry, don't want to work with you anymore, and get another person to take that person's place. And then obviously, if I've asked a test question, I get an observation about whether they do the right answer, and sometimes the workers may leave. And the reward is to maximize the expected value of the work questions, which is kind of weird because we actually can't observe what the reward is because we don't know the answers to those questions. Okay, so again, we use reinforcement learning. The state space is really simple. We basically have a model about how skilled the worker is and also what we call diligence, which means even skilled workers may stop paying attention and just start slacking off. So it's the cross product of those two different spaces. And we start out with the base policy, again, the sort of Crowdflower default policy, and then use sort of a pretty simple exploration-exploitation policy where we're using epsilon greedy, but we're decreasing the epsilon value as you spend more and more of your budget. That makes the system explore a lot at the beginning and then start doing its learned optimal policy afterwards. And here's an example of what we see. So as we start asking questions, we're doing just as well as the base Crowdflower policy. And then the system learns a better policy, and as it switches over to that, it starts being much more efficient with its resources. And the thing that's super great about this is it doesn't matter really what the optimal settings are, because it's going to figure out, given what the workers are doing, what really the best policy should be. So maybe it should be more strict than Crowdflower, maybe it should be more lenient, and maybe with some workers it should be asking more questions than others. So that's an AMAS paper. And then we also extended the model to put in adaptive learning as well. So like, how much should we teach the worker how to actually do the task? And what was really disappointing about that was that the policy the POMDP learned was really simple. It was basically keep teaching them and correcting them on their results until they get a certain number of answers correct in a row, which is like what Khan Academy does, and it's like the obvious policy. So you don't need a POMDP for that. Our POMDP did maybe a tiny, tiny bit better, but it wasn't interesting. Yeah.
Can I ask, what were you hoping to see? Like what kind of?
You know, afterward, well, that's why we stopped doing the research. It's like, well, that seems like a pretty obvious policy.
Because what we've seen is very consistent behavior. Like there's certainly like sort of a little poof up at the beginning as I'm learning how to do something, but after that, you actually have a pretty good bead on me. And it's not clear, like from our experiences, that I can really shift you one way or another. So it may just be that very quickly you can get a good signal and then dash from there.
I think that's a result. I think different people take different amounts of time to actually learn the task. But again, that policy of teaching them and correcting them when they make a mistake so that they actually learn what the task is until they get K correct in a row, which demonstrates they actually understand what they're supposed to be doing. That really simple policy works well no matter how quick a learner they are.
It might be possible to draw on some of like the interactive tutoring literature to think about like, well, which tasks, which trainings are we giving? Are we going to give you more and more difficult training examples as we go, sort of scaffold you up?
Absolutely, and obviously people in the education literature have looked at similar kinds of POMDP models. Of course, what they're really trying to do is make sure that they're maximizing for education, whereas in this model, we're trying to maximize for getting the most work done at a high quality, and education by itself is not so important or interesting. Okay, so that's one method. Now I want to switch to something completely different, and that is getting workers to argue with each other. So I'm going to introduce a bunch of a task, a relation annotation task, and I need to tell you a little bit about the task because it's actually a really hard task, and it doesn't sound that hard, but What we're trying to do is determine whether that natural language sentence, United States need to be ready to press compromise proposal, something Bush and his Secretary of State Condoleezza Rice show very little interest in doing. The question is, from that sentence, can we deduce that Bush lived in the United States? In NLP, we're interested in reading these natural language sentences and then building up a knowledge base of all of the facts that are entailed. One fact might be, did somebody live someplace? And part of the problem is that the Text Analytic Conference, which runs a competition on how well your natural language processing system does, has very complicated rules about what lived in means. So, for example, first of all, the fact that I know that George Bush lived in the United States is not enough. I have to be able to deduce it from the sentence. Secondly, if somebody works in a location, the TAC annotator people said, well, that doesn't let you, that's not enough information to conclude that they actually live there, because they may be commuting in from someplace else. On the other hand, if you're a national official, then you can conclude that you worked in that city, in that country, and so on. There's a bunch of other rules, and so to get high quality data, you need to learn all of these rules, and some of these sentences are kind of tricky. And what we notice is on these hard problems, if you do the standard majority vote, oftentimes the majority gets the answer wrong. And maybe there's only one person in the group that gets the answer right. And so our thought was, well, maybe instead of just aggregating by voting, we should have the workers argue with each other, and maybe one person can convince all the others that he or she was right, and sway the day. We could get higher accuracy that way. These problems are hard, as I said. Random is a binary question, would get 50% right. Using majority vote, you get 59% right. Using expectation maximization, weighted majority vote, you get 65% right. That's pathetic, right? I mean, it's really, really bad results. So the question is, can we do better? And hopefully argumentation is going to let us do better. So voting's bad. We don't like voting. Doesn't give us the results we like. So let's instead argue and see who sounds to be the best. And the basic idea here is inspired by the talk pages on Wikipedia, where people have a discussion about exactly what they should be doing. And the question is, can we actually put that into a microtask context and have these little discussions that are very focused and lead to better answers? So we come up with a set of primitive tasks. One is actually not new. It's the standard annotation task. Is like, given some judgment, mark it. Would you think it's true or false, or whatever? Another one is, well, now that you've decided it's true, can you explain a logical argument for why that's the case? That's the justify task. And then the final task is a reconsider task. So supposing I say the answer is true, I now want to have, the system is now going to present me a counter argument that is arguing the opposite position, and I get to see whether I want to change my mind after seeing that argument. So that's the basic setup. And so here's an example of the workflow. We start out with an assess task. They say false, and they give their assessment, and now they justify and explain why they think that answer is false. So we ask them what the reason is, and they write something down. Another worker comes in, they say true, and they justify with a different explanation. And then we go back and we connect these two workers asynchronously. And we ask them if they want to change their mind. Do they change their mind? And hopefully we get a better result. And then as more workers come in, we can do this better and better. So what's the hope? The hope is that we've got a whole bunch of people get the answers wrong, and one person who gets the answer right. And we hope that they're all going to switch over to the other side to give us the better answer. Furthermore, we hope we can do this without too much cost overhead from all of the arguing. Maybe we don't need to argue every time. Unfortunately, this is what we actually experienced, was that the bad people with the wrong arguments were just as good at convincing other people. And so there was like a tiny improvement in accuracy, but basically it was a complete miserable failure. So that was very disappointing. But luckily, we were able to figure out a fix, and that was basically to filter the workflow so that we only allowed people to do the reconsider tasks if their justifications were sophisticated. We call them discerning workers. So I've got a caricature here, but basically what we did is we looked at the Fleisch-Kincaid readability scores of what the workers wrote as they were going through the training process. And if their explanations were really kind of simple, then that was a clue to us that maybe they're writing simple explanations, maybe they can't really understand complicated justifications, so let's not include those people in the study, let's just conclude the others. So after doing that filtering test, we end up doing much, much better. So here's the standard results, 65% with EM, 71% with microtasks. So we did get some benefit with all the workers, but if we filter for just these discerning workers, we get up to 84%, which is really much, much better than plain voting at 65. So this was very exciting. And so in summary, here is the workflow. We got a training process, assess, and then this combination of justify and reconsider tasks. As going forward, we made two different extensions, and these are still in progress, but I think they're kind of cool. So the first one is in MicroTalk, what we do is we just select an explanation, a justification randomly, and present that to workers. But it stands to reason that a really good justification is going to be more convincing than just a randomly selected justification. And we actually wrote our own justifications and tried that, and the accuracy was much, much better. So the question is, can we somehow automatically find these best justifications or create them quickly and then use that to make the system work better? And so we tried, again, using a reinforcement learning technique, and we are, in fact, able to find the much more convincing explanations, and our system shows those much more frequently. As you can see, green means it's a really persuasive argument, and the height shows how many times we're showing it. So we're able to pretty quickly find the best explanations. Which is pretty cool. It took us longer than we had hoped, and so I'm not convinced that this is really a practical thing going forward. The other thing is, in the original system, when I come up with an argument, I write my justification, the counter argument I see is just this randomly selected, or maybe it's a good justification, but it has nothing to do with what I actually wrote as my argument. It'd be much better if I got something that was customized specifically to my argument, maybe pointing out a hole in my argument. So what we did was try to build a synchronous workflow that lined workers up so that they could debate with each other about the individual merits of their own arguments. And Jim Chen built this kind of cool chat interface with a real-time crowd source workflow that actually does this. And we seem to be getting much more focused arguments, but we're not sure whether, but it's also more expensive to actually bring workers together in real time. So it's not clear that there's going to be as much payoff as we'd hope for. The other thing we do is after they have an argument, they come to an agreement, then we ask them to go back and revise their justification so that we can use it going forward. So this brings me to the next part of a talk, which is thinking about how we can make these workflows actually improve themselves. Maybe we can have not just on the justifications, but the whole structure of the workflow, or maybe the instructions of the workflow, we can get the crowd workers to make these things work better. So as motivation, I want to pull out a paper that I did. It's actually a natural language processing paper. But again, we're trying to do relation extraction. And what most people do is for relation extraction is it's too expensive to actually go out there and ask crowd workers to annotate everything. So they use a method called distant supervision to generate heuristic training examples, which are kind of low quality, but they're better than random, and they actually allow the system to learn something pretty well. And a natural question seemed to be, because I did some of the early work on distance supervision, is maybe I could combine these two different methods and use mostly distance supervision, but infuse the distantly supervised training data with a little bit of crowdsourced data and get much better results. And so I decided to start working on that. And the first thing I did was a literature survey. And unfortunately, I found that 3 people had already written papers on the topic. So that was really disappointing. But then I looked at the results, and they all concluded it didn't work. They concluded that if we get the crowd workers to actually provide more hand-labeled data, it actually doesn't help over this really crummy heuristic. It just seemed really weird. So we looked more carefully at why their results were bad. And the reason their results were bad was because their training data was really bad. And they basically hadn't taught the workers how to do the task very well. And so the accuracy was about the exact same as this distantly supervised training data. So we thought more about how to actually do it and came up with a method called gated instruction. But it sounds kind of complicated, but it's really based on 2 key points. The first one is that workers don't read the instructions. Right? I mean, they just want to get on with the task. So the natural thing is we need to force them to read the instruction by making it so they can't actually progress in the workflow until they've demonstrated they actually read the instructions and understand. And then the second thing is when people write these instructions, usually they do a crummy job. And so the workers are legitimately confused about what they're supposed to do. So the obvious takeaway here is you should polish those instructions and make them really clear. And the thing is that just takes so long. It's really a pain in the neck. Most people doing crowdsourcing don't want to actually do that. So that leads to the question, can we get the crowd to actually do that for us? So again, here's sort of a standard workflow is we might start out with some instructions and teach the worker how to do the task. And then we're going to evaluate them to make sure that they really do understand the task. And if not, we'll go back and teach them some more. And then we'll go out and actually get some work done. What we're proposing, and this is Jonathan Bragg's PhD thesis, is a meta workflow which combines actions from the crowd workers with actions in the requester. So we're giving the requester a couple micro tasks to do too. One is to diagnose a confusion and then clarify the instructions. So the idea is come up with the initial instructions, we go through this until we detect some confusions, and then we ask the requester to fix those, and we go around that. Hopefully in this automated fashion, we can actually do it much faster and much easier. Here is as an example. So here's the task. Mark whether or not the image below is of a bird. Seems pretty clear, right? You want to ask workers, is it a bird or not a bird? What could possibly go wrong with this question? It's so obvious. We should just go off and put our $10,000 budget to get a bunch of birds labeled. Well, most of the bird pictures you look at are like pretty clearly birds or not birds, but it's only after you've gone through a couple hundred examples that suddenly you come up with that. Okay, is that a bird or not a bird? I don't know. Is that really, it is a bird, but is that really what you wanted me to label as a bird? What about that? Is that a bird? And so on. You have to see lots and lots of examples before you get to these corner cases. So in this workflow, we give the initial instructions an example, and then we ask the worker to basically not just say yes or no, but to explain where they are on the threshold. Is it a clear-cut case or is it an ambiguous case? And if it's ambiguous, then why are they confused? And then after we've had a bunch of workers go through it, we automatically cluster the examples based on the descriptions that people have written. And then we go back to the requester, and the requester sees a set of confusing images, and they have to decide for each of these clusters, are these positive examples or negative examples? What do I want it to be? And furthermore, they have the instructions there, so they can edit the instructions as they're going. So I might write, I want it to be a realistic thing of a living bird and put in some more examples. And then I can drag some examples from these clusters over and have them automatically inserted into the instructions to make it really clear, and also drag them over and have them put into the test examples that are part of the gated instruction before the worker can go on. And I can do this with all the training, with all the data I've seen so far, and then I can push, okay, I think I've got it unambiguous now, and then it goes back and it runs a couple hundred more workers through the tasks, but specifically it focuses on the ones that were confusing, and it picks out a couple examples from each cluster as well as a number of other examples randomly to see whether or not you've actually diminished the confusion substantially or not. That's the idea. And Jonathan is just starting the user studies on this. Okay, so now we're at the home stretch of the talk, and I'm going to say something pretty much completely different. So here, I want to get away from the training data, just trying to create high quality data, and instead think about the larger picture. So what we really want to do is optimize the behavior of the classifier independent of the data. So why is this a different thing? Okay, I'm repeating myself. So imagine that we're trying to label images and so on. We've got a budget. So I've got these pictures. One choice I could do is I could get one worker to annotate each of these examples. Another thing I could do is I could go out and use majority vote or something like that, get 3 workers to annotate each of these examples. As a result, I'm going to have much higher quality results, but obviously I've got a lot less data. So there's a real question about, should we do this sort of unilabeling thing, or should we actually get multiple votes? And if we're going to get multiple votes, maybe we should go whole hog and have one example and get it really, really accurate. Okay, well, that's obviously stupid, but it's not really clear what the right thing to do is in between. Most people are actually going out and getting 3 labels for every example, but is that really better? To figure this out, we got a bunch of different data sets, and then we simulated noisy annotations on the data sets, and then ran machine learning algorithm to try to figure out which of these strategies was better. And what we came up with was this. In half the domains, it was much better to get a single label. In another half of the domain, the other half of the domains, it was much better to get multiple people annotating things. And sometimes you wanted much more than 3. Sometimes you wanted as many as 7 people annotating the data. So that was very disheartening. I was really hoping it would be some sort of clear-cut thing. And furthermore, the differences are not insignificant. So you really can get a much, because again, this is the classifier performance. So if you can get a 5 or a 10% improvement in your classifier, if you're doing natural language research, that's super exciting. And if all you've done is change the way you're getting your training data, that's much better than having to go and learn how to use deep neural networks or something, right? Okay, so what's going on with this mystery? What we came up with eventually was realizing that there's 3 factors that affect what strategy you should be using. And the first one is, what's the inductive bias of your classifier? Specifically, what's the VC dimension of your classifier? Which is sort of a proxy for what's the dimensionality of your classifier. If you've got a high dimensional classifier that's either many, many features and it's a linear, or maybe it's a nonlinear classifier like a deep neural network, then relabeling is much more important. And the reason why is the classifier is much more able to overfit to errors in the training data. The second question is worker accuracy. And it turns out that relabeling is most important when your workers are just right in the middle. And it turns out if your workers are really bad, then it doesn't really matter what you do. If your workers are perfect, then clearly what you want to do is unilabel, because you're getting perfect labels, so there's no benefit. But if your workers are right in the middle, you can get a pretty big boost by doing relabeling. So it's not clear. You can't decide what to do just based on what your worker accuracy is, But all other things being equal, when you've got sort of these middling workers, then relabeling is more likely to be important. And then the final one is it really depends on what your budget is. So, and depending on what your budget is, you might want to do a very different strategy. So as you have more and more money to spend, what strategy do you think should dominate? How many people think unilabeling? How many people think as you got more money, we should get lots of people to label things? Yeah, that's what I thought too, but it's not. As you have more and more money, actually unilabeling becomes better and better, assuming that you've got enough training data. So why is that? So imagine that we've got a bunch of training points and there's some noise there. Intuitively, what happens is there's actually several different classifier boundaries that are consistent with that. So we could go out and ask to get these labels, these data points labeled multiple times. If we do, we're going to get rid of all the noise, but we still actually can't distinguish between those decision boundaries. If instead we go out and we get a lot more data points, then we still have noise, but actually because there's more points out there, it actually does a much better job of distinguishing between the different classifiers. It's a much more formal argument in the paper if people are interested, but that's sort of the intuition behind things. So that's kind of cool to characterize what's going on, but fundamentally it still leaves you guys in a quandary of like, what exactly should I do next time I'm actually trying to crowdsource things? You know, what should I do? What we'd like to do is have, be nice if there was, like, you didn't have to think about it at all. All you could do is use our off-the-shelf labeling strategy, and that's going to figure it out automatically. So what reactive learning does is like active learning in the sense that it uses the classifier's uncertainty to figure out what data point I should label, but it considers data points that have already been annotated and decides, should I get another label of that data point? And the first thing you might do is you might say, well, let's use some previously studied active learning algorithm like uncertainty sampling. And if you try that, it doesn't really work very well. Uncertainty sampling basically gets into infinite loops because it's uncertain about an example. It just goes and it asks, I want more and more. No matter how much data it can get about that example, it's never satisfied. There's ways of fixing uncertainty sampling so that it never gets more than a certain number of labels, but now the question is what's the parameter and so on. So uncertainty sampling by itself doesn't work so well. So again, we can think about this in terms of decision theory. Question is, which examples should we get? And without going into the details, the method that we came up with is called impact sampling. And what we do is we consider a set of labels, and then we say, well, suppose this label comes back as a positive. What's that going to do to my classifier? How many examples is that going to cause to flip in terms of the classifier's prediction? Suppose it actually comes back as a negative. How many examples is it going to flip? And then what's the probability it's going to come as a positive or a negative? And I can figure out what the expected impact is of that labeling or relabeling that data point. And impact sampling turns out to work really, really well. Again, there's a bunch of complicated things. The way I've described it, it's a myopic strategy, and you can't have a myopic strategy because suppose I've already gotten 3 examples or 4 examples. The one more example is not necessarily going to actually change the majority vote. So you need to sometimes think, well, maybe I should get a couple more examples on this thing. So there's a way of doing that without introducing combinatorial search, which we call pseudo look-ahead. Which helps enormously. Without going into more details, what you can see here is that impact sampling really works quite a bit better than any of the other methods. It is computationally expensive, so this method is especially good when generating the training data is also expensive or difficult to do. And if you're in that case, this is a fantastic technique. Some more examples where it does well. Okay, so in conclusion, what I've tried to argue is that this sort of decision theoretic method using partially observable decision processes and reinforcement learning is a really good way to think about any crowdsourcing interaction. And tried to introduce that in the context of a whole bunch of different workflows where there's different kinds of choices that the controller could make. So it could be what question to ask, how many times to ask it, how much teaching should we do, how much testing should we do, should we actually ask a person to argue or not. You can imagine facing all of these decisions using a decision theoretic method. And then as you're doing it, decision theory, you have to think what your utility function is, and there's sort of two natural different utility functions. One is how good is your data, especially important for test data. The other one is forget about the data. What I really care about is how good is the classifier that I'm learning. And then in general, what we're interested in is thinking about better ways of coming up with tasks that allow people to do what they're good at, allow computers to do what they're good at, and come up with these mixed initiative systems. And with that, I will stop and see if there's any questions. Thank you. Yeah.
You mentioned there were a couple bells and whistles on your algorithm that you didn't go into detail, but I think I'm missing the intuition. Why would the optimization that you're doing not have the same issue with staying uncertain and pressing one more labels for the same data point? Or rather, I guess I don't understand why the first one does that. If you're also doing...
Yeah, so what this is doing is it's saying, suppose I want to go back and label this data point X. If it came up as a positive, that would really swing my classifier. So that's why I really want to make sure I've got the right label. But the expected impact, that's weighted by how likely is it that it's actually going to come up positive. After I've labeled it a whole bunch of times and it's come up negative, 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 then the chance that it's going to come up positive is very, very small. And so it becomes not worth my, my trying to label it again.
Okay, so it's just not doing that modeling of the probability distribution in the first case.
In uncertainty sampling, the way that works is it basically just says, yeah, of all the examples, what's the one where I'm most confused? And what that usually does is it picks something that's right squarely in the decision boundary. Also tends to be oftentimes be examples that are very hard for people to label. But yeah. Yeah.
Would you say that I'm trying to explain the impact sampling, is it like deciding to campaign more in Pennsylvania than in California because the impact of flipping a vote in Pennsylvania would get me the outcome that I want, whereas
that's exactly what it's doing. It doesn't. It's not trying to win the election, but it's right. That's intuitively. It's trying to influence things. Yeah. Sorry, I'm going to switch to another slide. Yeah.
I was wondering, in terms of this vision of human and artificial intelligence, so what are the ways that you think you would bring humans into the loop, especially in the context of reinforcement learning? Like, have you thought about how do you have humans generate actions that are going to be taken? Is that you have humans provide more insight into what the objective function should be to be optimized? Or, one approach I'm interested in, and maybe you found it just isn't necessary, is having humans provide prior knowledge. So trying to actually have them in code knowledge about what actions to try out or what parts of space to explore.
I think all of those are important, and I'm really interested in all of those. I think the decision theoretic methods help you in some of them, but maybe not the most interesting ones. So, for example, I think really key thing is having the people involved specify the utility function or specify what the system is trying to do. I also think while oftentimes the system knows what, supposing we have some objective, the system knows what actions are actually going to be most effective towards that. But in many cases, you don't want to actually tell the person what to do. Maybe you want to allow the person to do whatever the heck they want to do because they're a person. And yet you still want to communicate to them that this is where their efforts are useful. So I think there's some interesting kinds of nudging techniques or visualization techniques that can guide people towards where they're most effective, but still give them the freedom to do what it is they want to do. It's especially important when you've got a bunch of experts as your crowd workers. Yeah.
I love the insight of treating the instructions as malleable in the task. I've always sort of viewed crowdsourcing task design as a user interface design problem, because it literally is. You're designing a user interface for the people who are trying to achieve it, and it seems incredible that I would I would never design an interface for something I was going to launch on the App Store and just launch it without ever showed it to people. But this is what people want to do sometimes with crowdsourcing. And so I really like this idea that I can that it comes back to me and I'm improving this interface as I go. And I wonder about, you gave one example which was around sort of edge cases that I didn't think about. Oh, like is a cooked turkey a bird? I'm wondering about sort of instances of classifier bias where it may be like essentially there would be total agreement, but it wasn't actually what I meant. So maybe intuitively everyone would consider the cartoon birds to be birds, but that's not actually what I intended. And I wonder if there are ways to sort of catch that kind of situation early, because that one seems much harder to detect. Because it seems like, oh, everyone's great, and maybe I'm even highly certain about it. We have examples where we're trying to annotate web pages with their position on, marijuana legalization as an example, and if there's a newspaper article that's reporting some pro-legalization argument, is that pro, or is it just someone reporting a pro event? Right? And these kinds of things like swing with very strong confidence, but are not at all what we intended. And I'm trying to think about how you can capture that into the workflow as well.
Yeah, I don't see if there's no ambiguity, then you're not going to pick up any signal from the workers, and I don't see any way of getting around that short of looking over all of the data or looking over a large sample of the data. But in all the examples I've seen in lots and lots of tasks, usually there is some ambiguity, and so some workers are confused. If I was confused and I hadn't thought about it, usually my instructions are going to be unclear on that example, and so usually this kind of strategy, my belief is that actually this will pick it up, although we need to actually see.
So given enough workers, all bugs are shallow, basically.
Say that again?
Given enough workers, all bugs are shallow.
I think that's a reasonable, yeah, that's a good summary.
So with your active learning approach that you did the last, what happens if I take the classifier that was generated in the dataset and with that same dataset I change the hyperparameters of the classifier, right? Because are the benefits still going to remain? Because you had implied that the amount of whether or not you want to have multiple labels is a function of whether or not how well the classifier is able to overfit on your data, right?
Yeah, so I'm sorry, I missed. Are you talking about the last part of the talk, the reactive learning? Okay, say your question again, because I was.
So if I take the generated, if I take through this active learning process, the data sets that was generated, right? And I change the classifier, are the benefits relative to just the naive approach is still going to remain?
Yeah, I think that's a really interesting point. It is specific to the classifier architecture, and that's specifically the benefit of it, is that it's going to get the data points which are best for that particular classifier architecture. If you then switch to a much higher dimensional classifier or a much lower dimensional classifier, then your data set's not going to be the optimal data set anymore. But I think there is no optimal data set for all classifiers, and so you should have made the right choice at the beginning. Or you can actually, I suppose you could imagine extending this where it's trying different classifier architectures as you go. Certainly the data points are going to be good starting points, so you could start out with that data and then train the different classifier and have it get more. It could then decide, I want to go back and relabel some things. There's no reason why you can't pick that up in the middle and keep going. Any other questions?
I also have a question, like, have you ever considered that, like, changing rewards based on your feedback of the worker and see how much that can affect the result of the workforce?
I think that there's a huge number of things that one can do in terms of changing the incentives, and there definitely are a number of people who've looked at that. We haven't really we haven't looked at that whole dimension, and I think that there are actually a lot of probably very strong interactions between some of the things we have studied and the incentive process. So yeah, much more stuff to be done. Yeah.
Question about, have you had any experiences with like unsupervised or semi-supervised problems where the labels themselves are not fully defined, they are actually, they evolve as you discover them? Like social science is plagued with this, that you have a psychology schema that is ill-defined, and as you get more data, you start defining it better and better, so the label becomes more precise as you actually see more data. But still, it's very hard to get like lots of data and lots of labels, so there's not one psychologist who has enough time to label them. I don't, this kind of like problem, like unsupervised or semi-supervised.
Yeah, so I think that's a really interesting problem. I think the part of our work that comes closest to that is the self-improving instructions. Again, where we use this sort of structured labeling process to try to identify where there's ambiguities in the labeling process, and then refine that. Yeah. Okay, great. Well, thank you, everybody. Appreciate it.